Today we're going to talk about graph theory, about what it is and where it's used. We're going to start getting some definitions for graph theory and making some pathways. Graph theory you may not have heard of before, but you have definitely seen it and used it with various things, I can guarantee. Let's see about some places graph theory is used. Any idea what this is? Well, probably most of you recognize that this is a subway map. We've got Grand Central here. We've got the Queensboro Bridge. So we're looking at New York City, a subway map. This is an example of graph theory. Another example of graph theory. Right here, some of you may recognize this. It's really blurry. That's okay. You don't need to read it. Do you recognize it as a family tree? If you do any type of genealogy, you will recognize that as showing, it says the descendants of James Carter. So if you've done genealogy, you've done a type of graph theory because you're mapping the pathways from person to person along a family line. Another example of graph theory. Anybody recognize that? Well, those are examples of molecules. So we use graph theory when we map the connections and pathways among elements that join together to make up our molecules in science. And here's another science example. This is kind of a bioweb. It's an example of graph theory because it shows how the food chain works for these animals that are in the same location. More examples of graph theory. If you are in computer science, you might recognize this spanning tree with different nodes of connection. If you're on social media much, you may have seen graph theory examples like this, where I've seen them where it talks about the words you use the most in your social media posts. This one connects different disease types and clusters, as well as words that join them and go along with discussing these different types of diseases. So that's a medical example of graph theory there. And my final example of graph theory, anybody recognize this? This is the fused connection map for an air conditioning system. It's the capacitor for an air conditioning system. You've got the thermostat over here, different settings, and it shows how the different parts are connected together. If you've ever worked on a car and gotten the manufacturer's book out, it will map the fuses and where the wiring all goes together if you need to troubleshoot things with your vehicle. Okay, so those are some really good examples of when we use graph theory. So hopefully you recognize that yes, graph theory is very present in all of our lives. It's just things that we take for granted. Graph theory is when we are showing connections between items, connections between people, connections between pieces of machinery. Used in many different fields though. Okay, let's get some definitions and look at some examples of what they mean. We're going to start with a vertex. A vertex is just a point. And if we're going to be plural, it would be vertices. If you've done any type of algebra and graphing, you've talked about vertices. If you've done geometry, we talk about vertices. You know that theoretically, the point has no dimension. It's infinitesimally small, but we have to represent it. So we have to draw it with some size. An edge is a line segment or a curve. So for example, if I have two vertices and I label them A and B, I can connect them with edges. Now, an edge can be a straight line segment or it could be a curve. So if I look at this, and let's just go this way. If I look at this, I have two vertices and I have three different edges that connect those two vertices. A graph consists of a finite, that means a fixed number, so it's not infinite, set of vertices and edges that start and end at vertices. So we've got a set of vertices and edges that start and end at those vertices. Edges don't just trail off into space. They have to begin and end at a vertex. And then a loop is an edge that starts and ends at the same vertex. Okay, so let's just draw an example of a graph with 3 vertices. I'm going to label my vertices A, B, and C. And I'm going to connect A to B and B to C with 1 edge each. And I want to connect A to C with 2 edges. So I'm going to draw a straight edge and a curved edge to show that I have 2 different pathways to get from A to C. And then I'm going to put a loop at B. Remember, a loop is an edge that begins and ends at the same vertex. So here I have 3 vertices, 1, 2, 3. And I have 1, 2, 3, 4, 5 edges. I have 1 edge that gets me from A to B, 1 edge that gets me from B to C, 2 different edges that get me from A to C, and I have a loop at B. When you think of a loop, think about maybe a room that has 2 different ways in and out. Or, you know what, we used to live in a house where we had a patio, a deck, and that deck had doors that opened onto the kitchen and the master bedroom. Okay? So my deck, if this is my deck, then I could go in and out there. All right. True or false? Edges cannot be curved. Well, that's obviously false because we have a curved edge right there. Number 3 says to use this graph to answer each question. Now, it gives us a number of things that we're supposed to like, we have 2 edges, 2 vertices. See if you can answer A through D on your own. Pause the video, answer those. Give me at least 2. I'm going to come back with all of the possibilities there. Okay, so let's look at this. I take it back. I did not list all the edges. I just listed 4 different edges. You might have listed an edge that I didn't list. I listed AC, which is right here. I listed AD right there, and I listed BD. I could have listed EC, CD, or either of those 2 ED edges. I also listed edge CC. Notice that I named it with both the starting and the stopping point at C because edge CC is a loop. Identify, it just said to identify 2. Hopefully you identified at least 2 of those vertices. And it's false that this graph has 8 vertices. It just has 5. It is also false that the graph has no loops. It has this loop CC right there. Notice that this edge ED or DE is not a loop. It's just an edge that happens to be curved. A loop starts and stops at the same place. So when I identify an edge, it has a different vertex for the starting point and the stopping point. When I identify a loop, it has the same vertex where it starts and stops. All right, let's talk about equivalent graphs. Equivalent graphs have to have the same number of vertices and be connected in the same way. For graphs to be equivalent, they have to have the same number of vertices and the same connections. So if I have, for example, for this graph, if I have 2 connections between E and D, if I were going to draw an equivalent graph to this graph, I need to represent both of those connections. Let's draw an equivalent graph to this one. That'll be good practice. So for this graph, I've got 5 vertices that are arranged kind of in a star pattern. Let's put them all on a straight line with each other. So we've got A, B, C, D, E. Okay, those are my 5 vertices. Now I need to represent every connection. I know I have a loop at C, so I'm going to go ahead and sketch that loop right there. Took care of that loop. That's done. I have connections from A to C and from A to D, but not A to B. So I go from A to C, and I need to go from A to D. I have a connection from B to D. So I should have ordered these maybe a little different. There's my connection from B to D. I got that one drawn. I have a connection from E to C. So there's that connection. I have a connection from C to D right there. And I have a connection for 2 different connections from E to D. So I need 2 edges that connect E to D. And I think that's all of my edges. 1, 2, 3, 4, 5, 6, 7 edges in a loop. 1, 2, 3, 4, 5, 6, 7 edges in a loop. Okay, so these are 2 equivalent graphs. They have the same number of vertices and the same connections. Look at number 5. Are these 2 graphs equivalent? Look at it and think about it, and then tell me why they are or why they're not. Well, hopefully you recognize that no, they're not equivalent. And they're not equivalent because this graph, the second graph, has more connections, more edges. What does it have that the first graph does not have? Well, it has this edge from A to C, and it has this edge from B to D. Those 2 edges don't exist on the first graph, so those 2 graphs are not equivalent. Okay, let's look at the next page. On number 6, for A and B, you're given 2 graphs and you're asked to draw an equivalent graph. Now we did this on the last page. We took our example graph and we drew an equivalent graph. Let's see if we can do it again. This one kind of makes me think of a house because of the way it's shaped, but it's not. It's just A, B, C, D, E. I'm going to suggest that you go ahead and put them in a line in order alphabetically, A, B, C, D, E, and then think about what connections you need to form, what edges you need to draw. Go ahead and pause the video, try that, and then come back and see how you did. Okay, so this is what my equivalent graph looks like. What I discovered was that if I start at A, and I just started at A because it's alphabetical, I can travel without picking up my pen. I can travel from A to B to C to D to E. So I can go straight without picking my pen from A to B to C to D to E. So I can draw straight through all of them. Then I look and I see that I haven't traveled, I haven't traced this edge from A to D. So I need to go back in and add that edge that goes from A to D. I can travel directly from A to B or from A to D. Okay, the second one, I'm asked to do another equivalent graph. This one is already in a straight line, so let's put it not in a straight line. I think that I'm going to make it kind of in a circle. I'm going to put my 1, 2, 3, 4, 5 vertices again in kind of a circle clockwise. I'm moving clockwise. So I've got A, B, C, D, E. Let's form the edges and connections again. Notice that we can do just what I did before. I can travel straight through A, B, C, D, E. So that's what I'm going to do first. I'm going to go A to B to C to D to E. Now it doesn't go back to, oh, it does go back to A. Look at that. I've got another edge out here from A to E. So I can go ahead and finish that off. Then I have 2 more edges that I haven't traced yet. I have an edge from A to C and an edge from A to D. So I need to sketch an edge from A to C and an edge from A to D. These 2 graphs are equivalent because they have the same number of vertices and the same connections. All right, solve this one. In a group of 8 friends, many have dated other members of the group, and then it gives you those dating relationships. What you're going to notice is that you have 4 boy names listed and 4 girl names listed. So let's set it up together, and then I'm going to pause the video and give you a chance to draw connections and see if ours match. We're going to draw a graph that models the dating relationships of the friends. So let's see. For our girls, we've got Phoebe, we've got Betty, we've got Claire, and we have Anne. So those are the 4 female names. And then we have some boy names. We've got Eric, we have Scott, we have Russell, and we have Matt. So those are our names. So those are our vertices that we want to represent. We have 8 vertices, and our edges are going to be those dating relationships. Pause the video, see what you can do with that. All right, we see that Phoebe has dated Eric, Scott, and Russell. So let's draw lines to that. Phoebe has dated Eric, Scott, and Russell. Betty has dated Scott. So we just draw one edge to represent that dating relationship. Claire has dated Eric and Russell. So we have 2 edges, one to Eric, one to Russell. Anne has dated all 4. So Anne has dated Eric, Scott, Russell, and Matt. All right, there is our graph that represents their dating relationships. Let's look at the next page. Number 8, we have a state model, and we have graph theory dealing with that. We have some rules set up. We want to show border relationships amongst the states. The states are represented by vertices. So we have 1, 2, 3, 4, 5, 6, 7, 8 states. So in each of our potential graphs, we have those 8 vertices. And if you look through, you see that every possibility, A, B, C, and D, have the correct 8 vertices. The vertices have been arranged in order so it makes sense with where they are located, where the states are located geographically toward each other. Nevada is the most eastern. Then I have Idaho, Utah, and Arizona kind of stacked vertically. And then I have these 4 states, Montana, West Virginia, oh my goodness, Wyoming, Colorado, and New Mexico vertically toward, this is west, this is east. I'm sorry, it's early this morning. So the states are represented by the vertices. If 2 states border or touch each other, then they should be connected by an edge. So if they border or touch each other, then we're going to connect them with an edge. Now there's a couple of different ways to approach this problem. The easiest way is to look for differences amongst the graphs to start narrowing down our possibilities. So instead of focusing on the map, I'm going to focus on the graphs. And what I notice first is that I have my major difference that I see first is that A and B only connect Montana to Wyoming, while C and D also connect Montana to Idaho. Which 2 are correct? Well, you can see that I could drive from Montana to Wyoming or Montana to Idaho. So my answer choices, I've just cut them in half. It's not going to be A or B. It has to be C or D. So now I look at C and D and I say, okay, well, what's the difference between C and D? These 2 graphs are almost identical, except graph C includes an edge, a connection from Idaho to Colorado that does not exist on graph D. So I go back to my map and I say, can I drive directly from Idaho into Colorado? Well, no, I can't. Idaho does not touch Colorado. I would have to go through either Wyoming or Utah to get from Idaho to Colorado. So that edge doesn't exist. My answer is D. Let's look at the next page. Number 9, I have a floor plan. So I've used graph theory with states and geography. Now I'm going to use it with a floor plan. We're going to use vertices to represent each of the rooms and a vertex for the outside, because you'll see we have doors out. You have doors from one room to the other, and you also have doors that go out. So we are just going to represent outside as one vertex. Because outside is just, outside's all connected. How about that? It's one big room. A door connects rooms, and our doors are going to be treated as edges. Anywhere we have a way to pass through a door, we represent that with an edge. Okay, you can set up your vertices in different orders. I'm going to kind of do it like this. So I'm going to say we've got the office, we've got the closet, and we've got the bedroom. Then we've got the living room, we've got the kitchen, And then I've got to decide, I'm going to put outdoors over here. So we've got office, closet, bedroom, living room, kitchen, outdoors. And then I want to use edges to represent every doorway. Well, kitchen is easy because it just has one door into the living room. So let's draw that. Bedroom is pretty easy. I can go from the bedroom to the closet or the living room. So I can go from the bedroom to the closet or the living room. If I'm in the closet, I can open the door into the bedroom, the living room, or the office. So if I'm in the closet, I've got an entry to the bedroom, the living room, or the office. If I'm in the office, I have that door to the closet or a doorway into the living room. Now let's check our living room. Our living room, I can go to the office, to the closet, to the kitchen, and I have 2 doors out of the living room. So the living room goes to out 2 different ways. Now I could have drawn this edge around the kitchen to represent the fact that this door is on the other side of the kitchen. That's fine. Either way would work. So I have 1, 2, 3, 4, 5, 6 vertices, and I have 1, 2, 3, 4, 5, 6, 7, 8 edges. Let's check and see if we have 8 doorways. I can see that I have 1, 2, 3, 4, 5, and then out would be my 6th place. I have 1, 2, 3, 4, 5, 6, 7, 8 doorways. So yep, I got all of my edges represented. Number 10 gives us some more definitions. The degree of a vertex is the number of edges that connect at that vertex. Now note, loops count twice as degree. If I have an odd number of edges that connect there, I have an odd vertex because it has an odd degree. An even vertex has an even degree. Adjacent vertices are vertices with at least one edge connecting them. So let's go up here and let's give the degree of each of our vertices. We don't have any loops here. Our outdoors has a degree of 2 because there are 2 edges. Living room is 1, 2, 3, 4, 5, 6th degree because see, I can leave the living room 6 different ways. Kitchen is just degree 1, bedroom is degree 2, closet is degree 1, 2, 3 because I can leave 3 different ways, office is degree 2 because I could leave 2 different ways. So we have 2 odd vertices, the kitchen and the closet, and we have 4 even vertices. Adjacent vertices are vertices with at least one edge connecting them. For example, the office is adjacent to the closet and the living room. The office is not adjacent to the kitchen or the outside or the bedroom because to get to those places from the office, I have to go through another vertex first. So the office is only adjacent to the closet and the living room. The kitchen is only adjacent to the living room. The bedroom is adjacent to both the closet and the living room, but it's not adjacent to the kitchen because I can't go there directly. All right, number 11, true or false? Loops contribute 1 to the degree. Well, that's false. A loop contributes 2 to the degree because if I have, let's just do a sketch. If I have 2 vertices, A and B, if I leave A, I can only go one way, so that's degree 1. If I leave B, however, I can go 1, 2, 3 directions, so that's degree 3. I have an edge and a loop at B. The loop contributes 2 to the degree. Okay, let's look at the next page and see what we're doing next. We're given a graph and used to answer questions 12 through 14 using that graph. I want you to pause the video, answer the questions, and then come back and see how you did. Okay, do your answers match mine? The vertices given, BE and H, are all 3rd degree vertices, which means they're all odd. If I go back and check vertex F, oh, I didn't answer that one. I left that one blank. H is odd. It's degree 3. What about F? Well, F, I can only leave 2 ways, so it's degree 2, so F is even degree. Sorry. Is vertex A adjacent to vertex B? Yes, because I can go directly from A to B. Is vertex A adjacent to vertex F? No. Is vertex A adjacent to vertex C? No, because to get to either F or C, I have to go through another vertex to get there. Now, we've been talking about paths without naming paths. A path is a sequence of adjacent vertices and the edges connecting them. If I'm following a path if I could put my pen down and start and just keep going without having to pick up my pen. Now, I can only change directions at a vertex. For example, on this graph, I can't leave C and then turn here to go to A. That doesn't work. I can't turn at a connection that's not a vertex, because that's just shows, well, you've seen how we've set up our vertices. Our vertices can be arranged in any order we want. Just because it looks like the paths are going to intersect doesn't mean they actually do. So you can only change directions at a vertex. A circuit is a path that begins and ends at the same vertex. So let's think about this. If you have 3 different errands to do, you have to stop and get milk, you have to mail a package at the mailbox store, and you have to go pick up dog food. So, and you have to go to the pet store to get dog food. So you have 3 different places to go. First of all, I'm probably going to try to minimize my time and distance, right? So I'm going to map out in my head the quickest and best, most direct route. So that would be the path from my house. I will leave my house. I will go to the maybe the pet store first because it's furthest away and I don't want the milk to spoil. And then I go to the mailbox store and then I go to the grocery store. That would be a path. But my path would leave me from my house to the grocery store. I hit all 3 errands in between, but I'm at the grocery store. A circuit, however, is a path that begins and ends at the same place. So if I start at my house, I go to the pet store, the mailbox store, the grocery store, and then I come back home so that I'm starting and ending at the same place. That is what we call a circuit. All right. Put a check in the appropriate box if the sequence describes a path and or a circuit. So the first thing you need to do is check the sequence. Does it actually work? Then you have to consider if it works, it's a path. If it is a path, it might be a circuit. If it's not a path, it can't be a circuit. Does that make sense? All right, so just looking through these, we have 3. We have 1, 2, 3. Does number 1 look like it could... Oh, well, let me ask this question differently. Which one of these 3 could not be a circuit? Well, number 2, it can't be a circuit because it does not begin and end at the same place. So we know it can't be a circuit. The other 2 can be circuits if they are paths because they begin and end at the same place. So let's check and see if they work. So number 1, can I go from B, A, D, E, A, B? So if I start at B, I can go A, D, E, A, and back to B. Yes, that's a path. It works. And since we start and stop at the same place, it's also a circuit. Let's try the next one. Does this work as a path? Can I start at D, go through these vertices in this order? So if I start at D and I go to F, G, back to D, and then to B. Yes, that is a path. Is that path a circuit? Well, no, because I started at one place and I ended at another. Okay, we have one more. Number 3, D, G, E, D. If I start at D, I can go to E. Oh, no, that was wrong. D to G, and then to E, and back to D. Yep, that works. That is a path that is also a circuit because it works as a path, and I'm starting and stopping at the same place. Look at number 17 on the next page. Answer those two, A and B, true or false. Every path is a circuit. Well, no, that's false, because I can start at one place and stop at another and it still work. Every circuit is a path. Well, yeah, that's true, because I have to be able to get from here to there. If I can get from here to there along a pathway and I'm starting and stopping at the same place, then it's a circuit. It reminds us of Venn diagrams. How do I draw a Venn diagram representing paths and circuits? Well, every circuit is a path. So I can say every circuit is a path, and I have the circles fitting inside each other, like a bullseye. Oh, sorry, you couldn't see very well. Let's look at 19. We have a couple more definitions about connected versus disconnected graphs. A connected graph is a graph that has a path connecting any two vertices. So if I set off, I can travel to all the vertices. I can travel edges to all the vertices. Nothing is cut off if it's a connected graph. If it's a disconnected graph, there's somewhere I can't get to without picking up my pen and moving to a different pathway. So I'm going to draw some examples of disconnected graphs. My first example of a disconnected graph, let's see, A, B, C, D. My first example of a disconnected graph is this. A is not connected. I can get from B to C to D and back to B, but I can't get over there to A. My second example of a disconnected graph is this, A, B, C, D, E, F, G, H. I can travel 4 vertices, or I could travel the other 4 vertices, but I can't get from this set of vertices to that set of vertices because they're not connected. My third example of a disconnected graph is this. That graph is disconnected. I can get from A to D and back, but I can't get to the other 2 vertices. I can get from C to B and back, but I can't get from the other 2 vertices. Because remember, I can't change direction where there's not a vertex. Let's do one more example of a disconnected graph. We'll make it just a little bit more complex. Just to remind you that you don't count intersections as a place to change direction if there's not a vertex there. These 2 graphs are disconnected. BDE is not connected to ACGF. I can't get from one set of vertices to the other. Look at the next page. Consider on 20 whether those graphs are connected or disconnected. I don't know why I have an error there. It shouldn't be there, but it is. Well, this first one is obviously disconnected, right? Because I can't get from this top part to this bottom triangle. But for B, I've drawn this extra edge, and now all of it is connected. I could start at A, and I could travel all of these edges and get to every vertex. When I have this single edge that connects one piece of a graph to another, and if I took it away, it would cause the graph to be disconnected, I call that edge a bridge. A bridge is an edge that if I remove it, it makes the graph disconnected. So this is my very first example that I'm pointing out to you of what a bridge is. This edge is a bridge. The first version of that, I had a disconnected graph. This time I just added this one edge and now it's connected. If I take it away again, I'm back over here and my graph is disconnected. It asks you to draw examples on 21. We usually do this in class. We do it so that everybody can see everybody else's examples. Draw an example of a graph that is connected and has at least 4 vertices. And then draw an example of a graph that is not connected and has at least 3 vertices. So I'm going to do my connected graph. I'm just going to label them A, B, C, D. And I'm going to do it like this. I'm going to do a loop at A. If I wanted to do degrees, A is 1, 2, 3, 4. 4th degree. B is degree 2, C is degree 2, and D is degree 2. That is a connected graph with 4 vertices. What about a graph that is disconnected, that is not connected and has at least 3 vertices? Well, you can do literally any number of things. Let's do A, B, C, D again, but this time we're going to leave something disconnected. Let's maybe connect this, and we're going to go around, but we're not actually going to touch C. This is a disconnected graph with 4 vertices. Okay, we talked about bridges. Look at this graph that we're given for number 23. If you take away edge QR, if I take this edge away, well, then if I took that edge away, I would have Q stuck out here by itself. And I would have T, R, S, and I've got a loop down here off of S. So if I took away edge QR, this is what I would be left with. And this graph is not connected. The original graph is connected. This graph is not, which means that QR was a bridge. For this graph, not only is QR a bridge, but RT would be a bridge because it's the only connection to T. And RS would be a bridge because it's the only connection to S, from S to the other vertices. Now, the only edge for this graph that is not a bridge is this loop. It is not a bridge. If I take the loop away, the graph is still connected. But if I take any of the other edges away, I have a disconnected graph. All right, number 24. Consider this graph. If I remove edge QR, and you can either redraw it or you can just think about it. If I remove edge QR, is the graph still connected? Well, yes, because QR is not a bridge. Let's go ahead and draw it. So we've got Q, we've got R, S, S has a loop, and then we have T over here. Because Q is also connected to T, if I take out QR, the graph is still connected. Look at this next graph. True or false, DE is a bridge. Well, that's false, because if I take out DE, E is still connected to both vertex A and vertex G. So we're still good there. Which of the edges on this graph is a bridge? Which edge, if I take it away, will disconnect part of my graph? Well, DH. DH is a bridge because if I erase it, suddenly H is not connected to anything else. Then it tells you to draw an example of a graph that has exactly one bridge. That's one example of a graph that has exactly one bridge. What do you look for to try to figure out that something is a bridge? Well, you have a bridge if there is only one edge that connects to a vertex. That's how I know I have a bridge.